According to a forming cyclone in the west of Sumatra, the Joint Typhoon Warning Center issued a tropical cyclone formation alert on April 26. Afterward, the storm slowly coalesced while moving northward and was upgraded to a deep depression on April 27. 6 hours later, the IMD upgraded the system to a cyclonic storm and named Fani. However, since the burst of Fani, its power has continued to intensify. To May 2nd, it was upgraded to a Category 4 equivalent cyclone by the JTWC. Whereas Fani started another period of rapid intensification, attaining 1 minute sustained winds of 250 km per hour, just below Category 5 equivalent cyclone intensity, and on May 3rd, it made a landfall near Odisha, located in eastern India, as a severe cyclonic storm, with 3 minutes sustained winds of 185 km per hour. It then swept across Bangladesh and disappeared over Bhutan on the May 5th. Fani is a tropical cyclone, the violent storm that originates over tropical oceans from where it draws the energy to develop. Tropical cyclone activity peaks in May and November in the North India basin, when the difference between temperatures aloft and sea surface temperatures is the greatest. The fuel for the tropical cyclone is provided by transferring water vapor and heat from the warm ocean to the overlying air, primarily by evaporation from the sea surface. Warm waters cause the overlying atmosphere to be unstable enough to sustain convection and thunderstorms. Moist air rises. Rapid cooling with height releases the heat of condensation that powers a tropical cyclone. In that case, high humidity is needed since when there's a great deal of moisture in the atmosphere, conditions are more favorable for disturbance to develop. Also, the Coriolis effect deflects winds blowing towards the low-pressure center and creates a circulation that maintains Fani's rotation. Fani has low-pressure center and clouds spiraling towards the eye wall surrounding the eye, the central part of the system where the weather usually is calm and free of clouds. The formation of Fani is not only associated with the atmosphere but also with the hydrosphere. It takes moisture from the sea to strengthen the storm, followed by the heavy rainfall and the storm surge led by the abnormal rise of seawater level during the cyclone. Besides, the passage of the tropical cyclone over the ocean causes the upper layers of the ocean to cool because the clouds may shield the ocean surface from sunlight, and the low temperature of falling rain can drop the seawater temperature. Fani caused 89 deaths in India and Bangladesh and the loss of $8.1 billion. Constructions at locations hit by the cyclone were extensively damaged, and infrastructure such as power supply stations were also affected. In addition, agriculture has also suffered huge attacks from Fani. It destroyed nearly 160,000 acres of farmland and cost $4.6 billion in damages. However, due to the excellent preparation and rescue work, various aspects of losses were minimized, especially in human costs. The Indian Meteorological Department issued alerts as early as Fani started to intensify, and the government immediately set up the evacuation of 1.2 million residents from coastal areas to cyclone shelters constructed in advance as the response to the warning. Rescuers and volunteers were also deployed ahead, and information about the arrival of Fani was continuously transmitted through television, radio, and text message. This work was a significant contribution to the reduction of loss of life from such events. It was a historic breakthrough compared with the damage caused by cyclones that made landfall in India in the past. Cyclone predictions are more accurate and fast with the development of meteorology, and we will be no longer afraid of such extreme weather events in the future.